Having discussed how the merge sort algorithm works, let's now try to analyze this algorithm. So going back to the description of the algorithm, if we denote the running time of merge sort on an input of size n by the function t of n, then we can write an expression for t of n by adding up the running times for each of these steps. So the running time for copying the first half of this array into a different array is just going to be some constant times. So this line is going to take some constant multiplied by n by 2 amount of time. This line is also going to take pretty much the same amount of time. And then when merge sort is invoked on arrays of half the original size, the time that the algorithm is going to take to run on these arrays is t of n by 2. And finally, we saw that when we merge together arrays of lengths p and q into a merged array A, the time that the merge procedure takes there is proportional to p plus q. And that's what we saw over here in a previous video. So p plus q, of course, here is nothing but n by 2 plus n by 2, because the values of p and q are n by 2. And so the time it takes to merge together the solutions to um, the time it takes to combine together the solutions to these two subproblems is some constant k prime multiplied by n by 2, sorry, multiplied by n. I'm deliberately choosing a different constant here from the constant over here because they need not be the same. So we can write t of n therefore as k times n by 2 plus k times n by 2 plus t of n by 2 plus t of n by 2 plus k prime times n. So that's going to evaluate twice of t of n by 2 plus k of n by 2 plus k of n by 2 is k of n, and k of n plus k prime of n is going to be k plus k prime, the whole thing multiplied by n, which is simply some constant, I'll just call it c, multiplied by n. So this is an expression for this is an equation for the running time of merge sort. And as you can see, because divide and conquer works by dividing the original problem into smaller subproblems, the expression for the running time is going to be expressed, the running time is going to be expressed in terms of itself, but invoked on smaller subproblems. So this is a recurrence equation for the running time. And that's what I've denoted here. Let me just call this C. T of n, the running time for merge sort, is equal to twice of T of n by 2 plus C times n. Now, how do you solve for this recurrence equation? In a later uh, chapter or in a later lecture, we're going to look at a theorem called Master's theorem, which will help you immediately write down the answer to recurrence equations of this form. But for now, I'm going to explain a different method for solving this recurrence equation. And this method is called the recursion tree method. what we do in the recursion tree method is we start with T of n, and then we replace T of n by the right hand side of the recurrence equation. Okay, so let me write down the recurrence equation here. T of n is twice of T of n by 2 plus C times n. So we are going to replace T of n by the right hand side, but we are going to, instead of just writing twice of T of n by 2 plus C times n over here, actually let me make this K instead of C because I've already um, incorporated the constant K over here. So, but instead of just replacing T of n by twice of T of n by 2 plus K times n, we will depict it diagrammatically in the form of this tree. So K times n is the cost, is part of the cost, and that's going to be depicted here. And T of n by 2 is the running time on the smaller subproblems, of which are half the size of the original problem. So both these smaller subproblems are denoted as the left and right child of k times n. So T of n is being replaced by the right hand side depicted in this particular way. Now the value of T of n is going to be the sum of the values of each of these terms, right, by definition. So k times n plus T of n by 2 plus T of n by 2 is equal to the value of T of n. Now in the next step of the recursion tree method, we are going to further open up these two nodes. Okay, we're going to replace T of n by 2 by the right hand side of the recurrence equation for T of n by 2. And what is the recurrence equation for T of n by 2? Well, we just replace n by n by 2. We substitute n by 2 in place of n everywhere here. So you get T of n by 2 is twice of T of n by 4 plus k times n by 2. So we'll replace T of n by 2 by k times n by 2, and then we'll have T of n by 4 as the left and right child of this node. And the same thing is done for this other node, T of n by 2. So again, once again, the sum of the values of all the nodes in this tree is equal to the original value of T of n. And that's actually the value that we want to compute. So what we are doing successively is we're going on opening up these T terms, and thus we sort of notice that everything here is expressed in terms of clean constants, right? So as we open up these terms, this whole tree is going to increase in its depth, and all these nodes are going to have constant values attached to them. And this process will continue until we hit the smallest possible size for the subproblem, which is simply a singleton array. Right, so we just continue this process over as many steps as needed until we hit the base case, which is T of 1. Now, how many levels will this final tree have? This is called the recursion tree, and let's assume that this is level 0. Let me call it level 0. Let me call this level as level 1. Let me call this level as level 2. So at level 1 we had two values, k times n by 2. At level 2 we had four values, k, each value being kn by 4. In level 3 we are going to have 8 values, all 8 of them being kn by 8. And in general, at level I, we are going to have 2 to the power I values, each value being kn divided by 2 to the power I. And this will continue until at the very final level, our values are going to be t of 1, of course. And how many how many such nodes will be there? How many such leaves will be there in the very last level? Well, that depends on what the height of this tree is. So let me call the level number of the very last level as h. So at level 0 you had just one node, at level 1 you had two nodes, at level 2 you had four nodes, at level I you had 2 to the power I nodes, at level h you're going to have 2 to the power h nodes. But what is the value of h? Well, for the argument of t to become 1, so the argument for t here was t of n. Right? And then when we created level 1, the argument was t of n by 2. The argument was n by 2. Then when we created the second level, the argument at the second level was n by 4. So at what height or at what depth will the argument become equal to 1? So the argument at depth I is n by 2 to the power I. The argument at depth h is going to be n by 2 to the power h. And we are saying that if h is the height of this tree, we are going to ultimately hit this base case where the argument has become equal to 1. Right? So when n by 2 to the power h becomes equal to 1, that will be our last level. Okay, so we can calculate what the value of h is. The value of h here is going to be log of n base 2. In general, in this course, we are going to assume that all our logarithms are log base 2 by default, unless we specifically mention that they are log base 10 or log base e. So I'm just going to denote h here as log of n. The base 2 is understood. So the number of uh, the value of the maximum level is going to be equal to log of n. And how many nodes are going to be there at level h? They're going to be 2 to the power h nodes. And because we know that h is log of n base 2, of course, this is simply equal to n. 2 to the power log of n base 2 is equal to n. So there are going to be n nodes here, each having a value equal to t of 1. So in order to calculate the value of t of n, we simply have to sum the values of every node in this recursion tree. And we can compute the sum of these costs level by level. Each of these values is basically a cost. And the overall value of t of n is simply the sum of these costs. So what is the cost at level 0? The cost at level 0 is kn, because there is only one node which has a cost of kn associated with it. At level 1 there are two nodes, each having a cost of kn by 2. So level 1 will also contribute k times n to the overall value of the running time. Likewise, level 2 will have 4 nodes, of each with cost kn by 4. And so the cost it will contribute is again k of n, k times n. Level I will have 2 to the power I nodes, each having a cost of kn by 2 to the power I. So again it will contribute kn. So each level is contributing kn. If you add the values on the nodes at each level, every level is contributing exactly the same, k times n, except for the very last level, because at the very last level we have n nodes, but the cost of each node is given by t of 1, whatever our base case value for t was. So actually in this recurrence relation, we are assuming here that the value of n is greater than 1. The value for the base case is simply going to be t of 1, which we can assume is, some constant. Let me call it C2. We don't know what that constant is, but we'll just call it C2 to differentiate it from this particular constant. So the last level therefore will contribute n times C2. So T of n is going to be kn plus kn plus kn. How many times? From 0 to levels h minus 1. So h times. And at the very last level, we're going to have a contribution of n times C2. Now h here is known to be log of n base 2. So T of n is going to be kn multiplied by log of n base 2 plus C2 times n. This is the value for T of n. Now in theta notation, we will drop the lower order terms. So there are two terms here. N times log n is in the first term and n in the second term. So the first term is clearly the dominant term here. So we can drop this lower order term, and in the dominant term again we can ignore the constant values, and so we can express T of n as theta of n log n. So this is the value of the running time in both the worst case and in the average case. Once again, you may note that the algorithm, the number of steps that the algorithm runs does not depend on the nature or the type of the input. It doesn't matter whether the array was sorted or reverse sorted, or whether it was a random or partially sorted array given as the input. We're going to execute the same number of steps the way we've written merge sort over here. And so both the average case time and the worst case time are going to be the same, because for every input of size n, the running time is exactly the same, and that's n log n. So to summarize, we have seen 4 algorithms so far: insertion sort, selection sort, bubble sort, and merge sort. The worst case time complexity of the first 3 first three were iterative algorithms. The worst case time complexity of all three were theta of n squared. The worst case complexity of the fourth algorithm, which is a divide and conquer based algorithm, a recursive algorithm. And you can see that the time complexity here is theta of n log n. Likewise, if you look at the average case time complexity, basically they're the same as the worst case time complexity. Theta of n squared for the first three algorithms and theta of n log n for merge sort. Now, one thing I want to add here is that even though merge sort has a better asymptotic time complexity compared to these three algorithms, it is possible that for small input sizes, merge sort may actually run slower than say insertion sort, which is typically fast for small inputs. So what I want to emphasize here is that we are guaranteed that merge sort will outperform all these three algorithms when n becomes very large. But for smaller values of n, it's not necessary that merge sort is going to be the best algorithm. In fact, you can see from the algorithm that we are creating these new arrays, we are making these recursive calls, and all that may take up a significant amount of time. It may, the value of the constant associated with the dominant term may actually be a very large constant. And the value of the constant associated with the dominant term here may be a relatively small constant, such that for smaller values of n, the values of the constants here may actually end up playing a significant role in deciding which algorithm is faster. So typically for smaller inputs, insertion sort works pretty well relative to merge sort. But since the asymptotic time complexity of merge sort is theta of n log n, which is better than theta of n squared, um, merge sort is eventually going to outperform insertion sort once the input size is large enough.